Hi students, here we're going to be looking at some antiderivatives and how to deal with them visually. We need something called slope fields to do this, and as usual your Khan Academy stuff will be up on your actual Jamboard. So we deal with this because we don't have ways to do antiderivatives directly for everything, and our goal is going to be to represent these visually with some slopes. So here we have an equation for dy dx, in other words the slope at a specific point is going to be x plus y. So what we're going to do is actually find these slopes by adding these coordinates together and see what happens. So we got -3, -2, -1, and 0. I'm going to close that so I can see this a little bit better. Then we got -2, -1, 0, and 1, -1, 0, 1, 2, 0, 1, 2, 3, 1, 2, 3, and 4. I'm not really going to differentiate between 1 and a 2. I am going to try to show some steepness change. So showing these slopes, so we'd have 0, and then we'd have a slope of 1, and a slope of 2. We'd have a slope of -1, and a slope of -2, a little bit steeper. Here's a slope of -3, slope of -2, slope of -1. This would be a slope of 0 again, and a slope of 1. What's going to end up happening are some patterns that occur, which will be a little bit weird. So we've got some slopes of -1 going on. We've got some slopes of 1 going on. This would be a slope of 2. That's terrible. There we go. And as we go further, we get steeper. These would be slopes of 0 as well. Okay, so this is a pretty good example of our slope field, and is a nice picture of what could be happening here. When we dive into these, we're going to talk about some specific places on this where we might be able to see a curve happening. So this will give us the general shape of something, and it might end up following something that looks something like this. As best we can, we try to kind of come up with ways to approximate the slopes along different places. Here we've got a couple of other slope fields for us to try. Please take a minute to try these on your own, and once we go through these, you're going to do some slope field activity stuff. Alright, so this tells me that the slope is equal to twice the height of the graph. So the slope, for example, when the height is 0 would be 0. At a height of 1, it would be 2. At a height of 2, it's going to be even steeper. And again, I'm doing the best I can to kind of get these. And then we're going to have the same type of thing going on where we start out less steep, and as we go down, we're going to go more steep. You might recognize that this, if we are kind of using these as, I think about them as train tracks, we're kind of coming down, and then when we get close to the x-axis, we're zeroing out. That looks like an exponential function to me, and in fact that would be. For number 6, we're looking at -y over x. 0, 0 would be undefined. In fact, any of the x points are going to be undefined. In this case, that's going to be a vertical slope, with the exception of at 0, but I'm not going to ask you to differentiate that. All of our y zeros that are not x zeros as well are going to be horizontal, because 0 divided by any other number would be 0. When our values are equal to each other, so like 1, 1, this is going to be a -1 slope. 2, 2 would be a -1 slope. And going backwards, we end up the same thing. And we have the opposite thing when these are opposite values. So we have positive 1s. When y is bigger, it's going to be steeper. And when x is bigger, it's going to be not as steep. So I'm just going to kind of sketch some of these things in. And again, you're welcome to do all these calculations. You can just kind of sketch them as best you can. I'm looking for positive slopes, negative slopes, zeros, and undefineds. And you might see something that looks like this in here. This might be some kind of a rational function, and that would make sense to me. There's an activity here. This is certainly be part of your workshop that lets you play with some slope fields and kind of see how they work. The last piece of this is to try to make some sense of which slope field goes with which differential equation. Differential equation is just another word for slope equation. So for example, I'm going to start with that one because that seems the easiest. So at a specific value like x equals 0, all slopes should be horizontal. So anywhere on the y-axis should be horizontal. I see it could be this one or it could be this one. When x equals 1, all slopes should be positive and have a slope of 1. That still works here. It still kind of works here. Yep, that's okay, or at least it looks kind of okay. And you might notice that as our slopes go more positive, they should be getting steeper. So 10 is going to go with B because these are steeper. And if you notice, we have a parabola here. X integrated, or the antiderivative of x, is going to be x squared over 2, so that makes sense to me. Looking at 2 minus y, so these are going to be things that when y equals 2 is going to be horizontal. The one that appears to have that is here, because when y is 2, that's horizontal, so that's going to be 9. I really like thinking about this for horizontal and verticals first, because that's a pretty easy place for us to find. For x minus y, when x equals y, we should have a slope of 0. So any place that's along the line y equals x, that looks like what's happening here. All of those are horizontal slopes. So that's going to be 8. And then sine of x, unsurprisingly, is the one that goes up and down repeatedly. So that's going to be 7 for us.